let's start from the primitive form. We have partial u partial t equal to u times partial u partial x, or plus u times partial u partial x equal to 0. All right. Okay, and let's draw a space-time diagram, x and t. And now let's draw a line that is like a straight line in space and time. And that line is that direction is a linear combination of space and time. So let's say this is a line that satisfies the criterion x equal to c times t. So when c is 0, x is equal to constant. That's a straight vertical line. If x is c, left. Okay, so let's analyze on that line. How does the solution change from one point to the next point? On that line, what is du dt? All right, if you restrict to that line, then the solution u on that line is just a function of time, right? Because space now depends on also time. So if you restrict yourself, focus yourself on that line, then solution u is a univariate function of time. What is du dt? Du dt on that line can be represented, let me write it more carefully, du of x and t on that line dt. So on that line, x is not a free variable. X is a function of t. So x is actually equal to ct. Okay, so it is du of ct and t with respect to t. So now if I expand it using chain rule, it is partial u partial x times dx dt, which is c, plus partial u partial t. Right? I mean, this is equal to c. And do we know what c has to be for this to be 0? If you look at the differential equation, if c is equal to u, then du dt equal to 0. Now, is it surprising that this line is a straight line? It is almost circular, right? So because if you have a line that locally has a slope of u, then the solution wouldn't change on that line. That means as you go forward, the solution is still u. That means the slope is still going to be the same as you track the line forward. All right, that is a little bit different if the right-hand side is not equal to 0. If the right-hand side is not equal to 0, you still have these lines going according to u. But now the slope is going to change because as you go along the line, then du dt would equal to the right-hand side, equal to s, right? We would still have characteristic lines, but then that line would curve. But for equations for the Berg's equation with 0 right-hand side, the lines are constant. The same analysis actually holds for any scalar conservation law. So if you have partial u partial t plus df du times partial u partial x is equal to 0, and you follow the same analysis, this is still the same and this is still the same, but in that case, what does c have to be? If c is equal to df du, exactly, or in general, then du dt equal to 0. The only thing you need is that df du is a function of u. which is true for conservation laws. The flux is a function of the solution. All right. Any questions? So for any general conservation laws, in smooth region of the solution where the primitive form would hold, then the contours in space-time would be a function of would be a straight line. And you know what the slopes are. The slopes is df du. In Berkeley's equation, df du is equal to u. For any conservation law, you can calculate df du as a function of u, and you know the slope of the contours. Now it is not surprising. Let's take a look at the Berkeley's equation again and magnify to full screen. Okay, so in regions where the solution is positive, the contours slope towards the right, because dx over dt is equal to u, right? Actually, if you look at the solution that is almost equal to 1, it is almost a 45-degree angle, because dx over dt is equal to 1. Now, if you look at this region where the solution is greenish, when the solution is equal to 0, we get straight vertical lines. This is where dx over dt is equal to 0. No matter what dt is, dx is almost equal to 0. We get 0 change in the x direction along these lines. When you have negative solution, dx over dt is negative, and when you get to -1, it's a negative 45 degrees angle. When we talk about the slope here, the slope is dx over dt, not dy over dx, as we normally interpret the slope. So it's a slope as you looking when you rotate your head. All right. Any questions on this? In general, the solution, the slope is not just equal to u. The slope is a function of u. But just in Berkeley's equation, because the flux has a special form u squared over 2, du dt is equal to u. So we get the slope is exactly equal to u. But in general, it's a function of u. All right. So now we know how the smooth region behaves. We can use that to predict the solution of the Berkeley's equation. So let's say at t equal to 0, the solution is a sinusoidal wave, as we were looking before. And this is top equal to 1, this is bottom equal to -1. We know the characteristics are going to be +1 here. We know it is going to be -1 here, and in the intermediate, the slopes are like this: smoothly change, and smoothly change from -1 to 1. And the solution along these lines are constant. So before these solutions would meet, I can analytically predict the solution, because if I follow the solution from here to here, I know the solution is from here to here is constant. I can draw a waveform that is basically a deformed version of the waveform at t equal to 0. It's basically squeezed together, right? So basically, we can analytically draw what the solution looks like based on the method of we call characteristics. These lines are characteristics. So x equal to ct plus x0, any line like that, where c is equal to df du, is called a characteristic line. So this is what characteristic lines are. They are the lines which, if you follow them, the solution is going to be a constant. If you don't have any source term. If you have a source term, if you follow the lines, the solution can be solved using an ordinary differential equation of du dt equal to s, right? So these are the lines along characteristic lines du dt equal to s. If s is equal to 0, you get constants.